right now we're looking at this, right? I want to know the Pentium 3 microprocessor x86, and that is true. With the Pentium 3, it has. So how you would solve this question? Most of these questions, it depends on whether it's true, but this one is absolute, something that you can verify. When you say yes, why is it true? Then you say that, oh, the x86 introduced pipelining, introduced data encode segmentation, data encode. The P6 architectures introduced. What did they introduce? Okay, I don't really. I want to say that was the first superscalar, um, the first implementation of superscalar architecture, but you don't quote me. So I want to say superscalar. Then you say that yes, it is true that the Pentium design is based on and this. For example, and the Pentium 3 has pipelining, has data and code segment. The P6 also has these features are present in it. Hope you get it. So basically, look for features online. Look for features. You can use these two features. It's fine. Just three features of P6 and your answer. Question this thing. Ish. I like everything was. So let's go again. Let's go again. Let's go again. So what I said is that the way you solve this question is by first the answer is yes. Answer is the way you solve this question is by saying why exactly that the Pentium 3 design is based. If something is based on this, you expect features to translate from them to see that the x86 introduced the world pipelining and data and right? The P6 introduced, as I said, don't quote me on this. I'm not really sure myself. I want to say superscale architecture because I know the first implementation architecture Pentium 1. I don't know whether that's why I'm saying that don't introduce the architecture to people. And these are all present in the Pentium. You can define these that these are the features that based on. Okay, if a microprocessor is built to using the same transistors and clock speed as now, it will be faster than the now peak. So this one it's in parts, right? It's parts. If the processor is built today with the same number of transistors, processor become a lot better than I think. I'm not really sure about a lot of these dates. It's a long time since I looked at just off the top of my head. Checking them. If it is built today using the same number of transistors and the original clock speed, see the clock speed will hamper the performance. What's built using the transistors will yeah, so we've gotten the original date for this, right? The time it ended in late 2003, early 2004. That's why. But then it actually started in 1999, and that was when the production. Understand? So if a microprocessor is built today, transistor fabrication processes are a lot better right now, right? And then if transistor fabrication processes are a lot better, that means that gates that are built on these transistors faster. So an adder that used to take, let's say, 0.2 nanoseconds to will probably right now take 0.0005 nanoseconds. Very, very possible. Very, very possible. With Moore's law too. Right? Moore's law. So there's this exponential graph in this world that is Moore's law. It talks about the fact that transistors increase in performance and efficiency doubles every year. So it's about getting to the time that that law will falls. But currently, it's still true, and it's just that year over year are better. Sometimes as twice as much as twice as the previous one. And so this is true. So meaning that transistors will be faster, but since your clock speed is the same, right, it will hamper your performance of your system. And so it's the thinking is like this, right? If, for example, uh, if for example, you have a fetch execute store cycle, right? And my fetch, the clock takes 10 seconds for fetch, 10 seconds for decode, seconds for execute, 10 seconds for. But the actual fetch finishes in 2 seconds because my transistors are faster. Two finishes in 1 second because the transistors are faster. The execute finishes in 5 seconds and this one finishes in 2 seconds, right? Even though they are faster, they will still have to obey the clock. You understand? And that gives you that hampers the performance of the system a little bit. So yes, if it's built with the same transistors and clock speeder, so you have to explain as I said, this my speed. As I said, these questions are justified questions. You have to justify why you are. There's no inherently right or wrong. The arguments that will make it right or wrong. Now B, you are tasked with the design of a new computer system. You're obligated to use either one permanent storage, temporary storage. One type. You cannot use other in it whatsoever, even externally. Which would you copy the effect of this choice? Okay. So we've come back to another question like what this question is basically asking you is that what is the best between or differentiate between permanent storages and temporary storage? That's what this question is basically asking. So you have to pick one. So let's go. So for example, if I pick a hard disk drive, that advantages hard disk drive, so like more storage, be able to store more things. Second advantage is that it's a permanent storage. So meaning that if the light goes off or like the electricity goes out, the electricity is cut, right? My data that I was working on will still be kept. The disadvantages of this system is that it will be very, very slow. Very, very slow. You can't use this thing, you can't connect this one to a microprocessor and expect it to be as fast as normal storages. It won't be, you understand? It just won't be. This is because with permanent storages, right? Um, the So permanent storages mostly are optical disk right now, CD. If you've ever had a chance to open a CD, a hard disk case before, you see that just a CD with the laser pointer thing just moving around. And that's basically happening. So what this means is that it will give you slower accessing and indexing speeds. At the time that it will take index and access your memory lower than just using faster memories like registers. You understand? So what are the advantages of RAM? The advantage of RAM is that it will be very, very fast. Very, very fast. The disadvantages of RAM is that it's volatile, meaning that if light goes off, okay, oh, all information is lost. Understand? So those are the disadvantages. So it is your choice, pick one. So you can say that, oh, I will pick RAM because with the new computer system I'm working on, it doesn't need to have a lot of storage and the information that will and where we are using the laptop to it has higher it doesn't have any chance of ever getting light out. You understand? So you can pick that one. Or you can say that HDDs are like your system, the new computer system that you are designing needs more storage. It needs to be durable. It needs to have volatile memory. With it, at the cost of speed. And then the effect of the choice is what you justify. You say that, oh, even though RAM is very, very volatile, like RAM is, even though RAM is very, very fast, it is volatile. That's the effect of it. Even though HDD is very, very like large, has is a permanent storage. Okay, cool. We are back. We're working on this C question. We're comparing single core microprocessor with a 10 gigahertz clock and a 5 core microprocessor with 10 gigahertz clock. So we have single core 10 gigahertz gigahertz 10 gigahertz microprocessor, and you have a quad core 2.5 gigahertz microprocessor. You're looking for the better of them in terms of design. Okay. So what does this mean? So if for example, let's go this way, right? If for example I had 10 giga of instructions, I had 10 billion instructions, 10 billion instructions, and I ran it on a 10 gigahertz clock. It will take 1 second to run all the 10 gigahertz of instructions. If I run the same 10 gigahertz of instructions, 2.5 gigahertz microprocessor, what will happen is that a quad core 2.5 microprocessor, what will happen is that if the instructions are optimized for um multiple cores, right? What will happen is instructions will be split up in some form or the way, but what you expect is that 2.5 of the instructions will come here, 2.5 will come here, 2.5 will also come here, and 2.5 will also come here, giving you the same 1 second, right? Same 1 second of time. Right now, you have to analyze it from the core side. Which one is more effective? And they're talking about it in terms of design. Design means performance, right? If I had to stretch both of these to their limits, which one would give me the best performance? And um, the way you answer this question, they see this question, it's not really a justifying question per se, but you have to justify it. With the 10 giga what you experience is heat, a lot of heat. Hey, a lot of heat. There's a lot of heat because it's running very very fast. Your clock is going very very fast, and the faster your clock, more speed that you in, and your system will be faster, but the more heat that your system will also, the entropy of information. Okay, then yes, so it would work with, it would it would heat up very very quickly. Let's go with that one. And for the 2.5 giga this side, and what will happen is that if your system is not optimized for using the 4 cores, because there's some programs that exist that cannot be separated up and run. A classic example I always use, right, is the prime number question. If I write code for a computer to find out for me what like find out for me the largest prime number they absolutely, what will happen is that they will start off, and then for example, let's say it starts at 10. So you have to generate all the numbers from 1. Okay, let's go from 2 to 10. Okay, so 2 to 9. Then after that, you have to divide 10 by all the numbers. And if it finds 1 hour, that's like contravenes, like it's actually enters sorry, it actually divides evenly, right? You would have to pause it and say that, oh no, then you're not a prime number, and then move on to the next one. With that kind of work, you cannot split it up, you cannot branch it out, you cannot do any predictive tricks on it. You understand? You would have to follow it to the end. With that one, with that particular question here, you only optimize 2.5 giga. Like you only optimize one core. The other cores will be redundant. You understand? Because it's a sequential, the program is sequential, right? Where the different where the different cores will come into play is when your program is optimized for using them, right? So can your program be split up into multiple tasks that can be performed by individual cores? That's the question that the multi-core programmer must ask himself, right? This task here, can I separate it up into various tasks that each core can perform? You understand? So if your program is not optimized for using all the 4 cores, a waste. And that means that if I have to run 10 gig of instructions, right? 10 gig of instructions will take 1 second on this single core gigahertz, right? But if it's not optimized, then your 10 giga take 4 seconds. That means 4 times as slow as 4 4 times as slow as your your single core 10 gigahertz clock. I hope you understand. So that would have to be the way you frame it. There's no right answer with which of the following is. You have to, it's a defense. You have to defend it. So if you check, these questions are already the class groups. Let us move. So okay, cool. As I said, this is the question that we think will come. So let us look at it with or D. See, we've come back with the justify questions again, right? Right. So it says that using the ideas from the architecture of 8086 microprocessor or otherwise, how could we design a system based on this processor that is capable of addressing up to 4 kilobytes of main memory? Very, very interesting question, right? So everybody, like right now, I'm sure you know that the x86 has 16-bit data bus, right? It has 16-bit data bus, but it has four extra lines that are used for it's um called addressing offset. You understand? So if you want to address anything here, if you want to address anything, would add the 16 lines to 4 lines, you get 20 different lines. Then we'll run a data on it. So it can actually like access 1 megabyte, 1 full megabyte of memory. And so it has offsets. Basically, it has offsets. Extra lines that do nothing. If you're running data, try to use the 16 lines, and if you're running address it to use all the 20 lines. Hope you understand. So this is how the x86 is able to address the yes, able to address 1 megabyte of memory, able to access the able to address the 1 megabyte of memory. So here he's saying that what is the usual maximum address for an 8-bit processor? Right. So for an 8-bit processor, you see the usually the number of address lines equal to the number of data lines. Right. So if you have an AD line like number of 8, have a data line number of also 8 in the usual case because they use the word usual. Understand? So we'll go with the same S is equal to AW formula. So not to assume some things, please don't play with the assumptions. Be sure to like write down the assumptions for him. Even if it is wrong self, as long as even if you are like it doesn't answer the question or you deviate from the question, as long as your assumptions are correct, I believe that you will get some marks. That's if he marks. If Chris marks, electrical, you know yourself. Excellent. So S is equal to A times W. First of all, you have to assume that your MIP is byte addressable. And that's what we do, right? Like if for example today you hear if an addressing question comes, that will come. If it comes in, if we say something is byte addressable, that means that for each the width of your data in your system is equal to 1 byte, right? You'll be able to get some marks with that information. So let's move on. You write assuming the microprocessor is byte addressable. And also have to assume that your data lines have the same, like they are equal to the number of address lines in your system. These are the two assumptions you have to make. Right? Now, when you make these two assumptions, you can find out the size of your microprocessor, the storage. You have 2 raised to the power 8 times 1 byte, give you 256. That's right, 256 bytes. Okay, so that's the usual maximum addressable memory, 256 bytes. Now it says that you want to address 4 kilobytes of memory. What is 4 kilobytes of memory? 4 kilobytes of memory give you raised to the power 2 times raised to the power 10 times 1 byte. That will give you raised to the power 12 bytes. So that means that you need 12 lines to run. If you have 12 lines, you can address 4 kilobytes of memory. But we have 8 lines in this system, right? So if you remember, we use the x86 concept of line offset, right? We'll have some lines for running data. We have 8 lines running data. 8, and then would have 12 lines. We have 4 more lines, right, as line offsets. I hope you understand. With this one, you'll be able to address 4 kilobytes of memory. Now, this is so using ideas. This is the idea we use from 886, right? Very, very simple. We don't want to move to other like architecture because it will be more complex. The way that um microcontroller would access more memory, it has a unique way of accessing more memory, right? So it has a certain number of address pins. I don't talk about it, but I'm just mentioning that you can have an idea. Maybe to help me in a question, right? So the way that a microcontroller, see, a microcontroller is just there like that. It has plenty pins. But I've forgotten the exact number. 32. It has plenty pins on itself. Ground pins, power pins, address pins, a lot of things, maximum and minimum mode pins. Right. What happens is that the you use the lowest one for addressing. I think the lowest how use it for addressing, the lowest 8. I think it's okay. When I last saw you, we wanted to talk about the interrupts. Yes, the interrupts. So this question from various sources, right? I believe this will be the question. Various sources means like from what I've thought about, you know, I'm not going to ask anybody. Nobody's speaking of our boss. So we'll have to maintain with it is still with great. I have to add the disclaimer like this is still with great question. If this is the question that would come. Let's look at it with mind. Or you can just wait for me to finish and then just take screenshot of the video and then you shoot and then write. That's also an option. Any of those two. Okay, let's go. Right. If um device one interrupts the microprocessor and the time. So if device one interrupts your system, it will take, according to this table, it will take 2 seconds, right, to solve this problem. So yesterday when I was explaining, I explained exactly how interrupts work, but let me go over it again so you can have an idea of it. Calvin said that he also feels that what is an interrupt will come. So please have it in mind of what is polling or trying to explain what polling is because he taught us directly. That might not be subject to the past question. Please just think about it. So back to the thing, right? Let's take it like this, right? Let's take that you're going to buy watching, and then if you go and buy the watching, there are 3 levels of priority, right? The watcher seller's daughter, because you can never have priority more than the watcher seller's daughter. And the rich homie who always comes to buy plenty, and then you are the last on the priority list. So this is what polling, this is what interrupts means. Interrupts means that um you yourself, like you are there, right? You are the lowest priority, this priority, you are priority 5, this priority 3, this first priority, right? You come and buy wachi, and then the wachi seller's daughter comes. You don't think that like you come with an issue, right? You want to come and buy wachi, you come to the wachi seller that you come to buy wachi. The wachi daughter comes. Don't imagine that you get served. You obviously serve the daughter first before you. Or if the rich homie comes, they have been buying less than 10 CDs. But he comes to come and spend, comes to talk with the woman, play music, those things. Right? So you don't expect that you have a high priority than him. You don't expect that like you served earlier than any of them. Even though you came first, it doesn't matter. You understand? So what if the analogy, how we relate this analogy to this is that 10 minutes, buy your watch and everything in it. It will take device one, take the watch seller's daughter maybe 5 minutes, take the rich home maybe 17 minutes. Right? The times are arbitrary. It doesn't really matter. It doesn't depend on anything. It can be just how it is. Right? So we have these three analogies in the system. The watch daughter, the rich homie, and then you of course. So with this information here, if I ask you that, this is the remainder of the question. The remainder of the question is, let's call it into it. right? So if I ask you that, what will be the time it will take, right? What will be the longest time that if I ask what will be the longest time that, so please sorry for the stereotypical name I'm about to use, but what will be the longest time that Auntie Mansa's daughter will have to wait? That's the question that we are asking, right? Like the watcher daughter is the first in the priority list, right? When anybody comes, like when you go, when the rich homie comes, be the first on the list. They will serve her first. No matter anything that is happening, no matter your level of priority. Maybe you've not eaten for 3 days, that doesn't matter. You understand? No matter anything, the watcher daughter, because she's first in priority, should be served first. Excellent. So we're asking that how will be the longest time that the watcher daughter will ever have to wait in this life for watching. The thing is that device 2 takes 17 minutes and device 5 takes 10 minutes. So you're looking at it, we have to look at it in the worst case scenario. In the best case scenario, so let's look at it in two forms, right? The best case scenario, in the best case scenario, the watching daughter, like they just open the shop and the watching daughter came, meaning that she will take 0 seconds. And she's the highest priority, so it will take 0 seconds for her to come and buy the watch. You can't see anything, right? Came first, and then there was nobody around. When she came first and she had high priority, it will take 0 seconds. But what in the worst case scenario, Auntie Mansa just picked a bowl and started spooning in. So in the worst case scenario, Auntie Mansa just picked a bowl and started spooning in any of these people. So like common courtesy is there, right? We have nepotism and we have common courtesy. So if personally I go and then she picks the bowl and she picks the ladle and then she's about to spoon the watch into my bowl, and then the daughter comes up, she won't stop. Like she just started the process of giving me watch, so she can't stop and then give um the daughter priority. You understand? That is not done. And the interrupt is the same thing. When I just start the process, when an interrupt pin comes, the second I start the process and the interrupt pin comes, it will have to wait for me to finish my process before it's started. You understand? That's what the interrupt mean. So in the worst case scenario, um device 2 device 2 just started, right? Because it has the worst time to device 2 in the worst case scenario, because in the worst case scenario, in the worst case scenario, right? In the best case scenario, device 5 is the only one that is in the queue, and like that's like they will serve them first, right? But in the worst case scenario, device 4, device 3, device 2, like they are all in the worst case scenario, they can all just have started processes. If device 4 starts, just immediately starts its process and device 5 has an emergency, it will wait for 2.5 nanoseconds before it can attend to device 5. You understand? If device 3 has started that, it will have to wait for 0.92 nanoseconds. If device 2 starts, right, just starts his subroutine, and then um device 5 gets an emergency, it will have to wait for 1.2 nanoseconds. In the worst case, device 4 has started a routine, and then they brought device 5 and an emergency. I hope you understand, right? So we compare this back to the watcher seller algorithm. What will happen when things come? So the thing is that if rich homie comes into the equation, as rich homie comes to meet me, and no matter like the second rich homie's car arrives, I just told the man, Pachompe, watch 2 CDs. You understand? At that particular point, the process of giving me watch has begun. So regardless that rich homie has come and the woman wants to get more money by serving rich homie, get tips and everything, it still won't happen because you can't interrupt a process that is in the middle. Understand? That's basically what will happen. So that's what happens in this system. Beautiful. So the next question basically is asking you. So we just talked about the yes. So what did we exactly? What question exactly do we answer? That's an important question to answer to. So what did we just answer? Excellent. So we just answered the longest possible wait time to run a subroutine for the highest priority device, right? So we looked at it and we said that, oh, looking at the fact that I just came, right? And Timansa would have to wait for me to finish before she can attend to her daughter. So meaning that you have to look through the how much time everybody will take. Because in the worst case scenario, like it can be that um on this day when she came, there was nobody there, so she took 0 seconds. It can be on the next day when she came, reach home was then reach home takes just 2 minutes. So in 2 minutes he was gone. It can be that when um she came, I was there. So this the probability people. There's the sample space. Right? There's the set of all probable outcomes. It can be that it took 0 seconds when she was there. It can be that, so what's the worst of them all? That's the question you're asking yourself right now. You understand? So we look at the question again. When we're having the question, we look at it this way. You say that looking at this thing here, what is the sample space if I am the highest? The highest priority is device five. I hope you know that's on the question. So device five, what's the longest time device five will have to wait? Well, if device five comes when one is started the process, you have to wait 2 seconds. If device five has an emergency or has an interrupt when or sends out an interrupt, sorry, when device two just started, it will have to wait 1.2 nanoseconds. But if device five, you have to wait 0. And 2.5. So what is the worst time? That's how we determine like what's the longest time, you understand? That's 2.5 nanoseconds. I hope you understand. This one is really on my heart. Okay, so they're telling you that yes, they also included using an interrupt based system. We'll get to the polling soon. And so what if you are the lowest priority? Right? What if you're the lowest priority and you're assuming the best case scenario for you being the lowest priority is that when you went, nobody was there. The master's daughter was nowhere to be found. Rich homie too was nowhere to be found. So you 0 seconds. In the worst case, then you've really made shit. Right? The worst case, then that means that Antimancer's daughter just began an interrupt, and then and so like it's like you're going to join queue now, right? The queue too. It's not like who you have you have priority over. It's people who have priority more than you. So you have Antimancer's daughter as the first person, Rich Homie as the second, and you are last in line. This is the worst absolute case. Like this like the day wasn't going well. This is the worst absolute. That means that you have to calculate the time to take for daughter to buy her food, and then the time to take for rich homie to also buy his food. That's the entire waiting time that you have to wait for you to be served. You understand? So when we get back to this question here, when we get back to this question, when we get back to this question, we see that the lowest priority device is device one. Right? So in the worst case scenario, device one will have to wait for. So we assume that device 5 had just had a meltdown, had a problem. Device 4 also has a problem. 3 and 2 has a problem. That's the absolute worst case. That sort of they're in a queue and device 1 is at the back of the queue. You understand? So something like this. So it will have to wait for time taken to run 5 device 5's ISR is 0.1 plus device 4's is 2. So uh, So last previously on this stream, as we calculated the timeline to take for the lowest priority interrupt, like the longest timeline to take for the lowest priority interrupt to wait for a service. Understand? So we can relate to it just also hits me that for those who might not be enjoying the watching metaphor, we can go with the car metaphor, right? Garage. The father owns the garage, right? And then or a store, right? You don't wait in line, you don't wait in line. Like you don't wait in line. Father owns garage when you brought your car. Like you won't wait line. But if you go someday, right, and then they're working on like any person, regardless of priority, any person's car, you will have to wait for them to finish that one because common courtesy dictates that you are not like you don't just skip people. You understand? Common courtesy dictates. So you have to wait for them to finish servicing the person's car and then they'll move on to you, regardless of whether like any people came. Because if father owns the car, you have priority. You understand? You really have priority. So job applications too can be another analogy. So you can think about it in any way that makes you comfortable. Right? That makes you like they're in the middle of an interview and then the owner of the company comes. Like the son of the owner of the company comes. Right? They cannot stop the interview, but any other person who is after that guy, will have to like wait for the owner to be served, the owner's son to be served. You understand? That's how you think about interrupting a routine. Four. Yes, we calculated 4.72 as the worst time it will take for an interrupt-based system, the lowest priority in an interrupt-based system is served. Right? And it asks you again that what is the longest possible waiting period? So there's a reason why I've been doing the best waiting period or the shortest waiting period and then the longest, right? If the question goes like calculate the shortest waiting period, you already know what to do because we already talked about it. And please, I'm very, very sorry if I'm speaking. I seem to be speaking fast and I'm not getting it's one, yeah, I want to cover a lot. Like instead of going through the slides, and this question gives you an idea of what can come. Let's move. Calculate the longest possible waiting period. Run a subroutine for the highest and lowest priority device using a polling based system. This it. Um, so this is what is happening in this case. What is happening in this case is that so let's explain polling. Let's explain polling. Let's explain polling. Right? Polling is how do I even put it? It's an IO interfacing technique. Let's go that way. Not really like IO interfacing, but like it's a way of communicating with IO devices, right? Where the microprocessor is what is the boss now. As you see, in every other one, the microprocessor is like everybody's child. You understand? It's at the mercy of everybody. It has to wait for sensor data. Else nothing can you can't do anything. You understand? That's with the interface. Now with polling, right? With polling, what happens is that the microprocessor will go and see, hello, will take device one. Right? It will go to device one and say, hello, what is up? Like, are you good? If device one says no, I'm not good, then it will run an ISR, it will run a routine, make sure device one is good. Then to go to device two and say that actually, how be? If device two says that I'm good, it will move on to device three. It will ask device three the same question. Device three says that I'm having a few problems with this, it will solve the problem, then to go on to device four and ask device four how so that's basically what the microprocessor is doing. It is asking, polling in the sense that like election polls, right? It is asking, what do you want? Who do you want as a president? My president is asking that, are you fine? Like, give me data. Give me data on what you are doing at the moment. Right? Device two to have give me data. So, for example, let's say that Dr. Yankee used this in the electrical biomed joint class, right? He says that a water like a water sensor, like something a closed water, and it is connected to acidity, not the amount of debris, and something like what else can we? I'm really out of ideas. So the microbes in the amount of microbes in the system, right? So this is debris, this is acidity, this is stability. So what the microprocessor will do is that it will ask debris, give me information. Right? If it realizes that the debris, the value and the debris sensor got was too high, it will do something. It will run an ISR, it will run its service routine, make sure everything returns back to normal. Then it will ask acidity, sir. Then acidity will give its value. Then it will say that acidity, you are fine. Then to move on to stability. Then it moves on to stability, and stability gives a certain value. It says that um I'm not really too fine. Something is going on. That's when like it will also run an ISR. So that's what the polling is that it asks the sensors to give it data, and the interrupts that the sensors are actually giving the microprocessor data. You understand? That's what basically happens. Excellent. So now we have a framework to answer our question. Okay. So it's asking you that given this given the time that indicated in the table below, what will be the longest waiting period that any polling have to wait? So, for example, what the question is basically asking is that, right? Hello, I want to poll something. I want to poll the devices in my environment. I want to poll all these devices. What's the longest time that the highest priority device will have to wait? So this is what happens, right? What happens is that because of priority, so because of priority, it will pull device 5 first, then go to device 4, device 3, device 2, device 1, and then it will begin all over again. This is what happens. And this is what happens. So the microprocessor will ask device 5, what's up? And the device 5 will give it information. Anything needs to be done, it's run an ISR. Device 4, are you good? Anything needs to be done, ISR. So this is the path. This is what happens. Right? What will be the longest time that device 5 will ever have to wait? In the worst case scenario, device 5 just ended. Device 5's cooling just ended and had an issue. Understand? So how this can be explained is that okay, so let's go this way, right? So I try to use examples as close to my environment as possible to make sure everybody understands. So let's assume that you have three friends. Isaac Bona. Isaac Bona is friend number one. Kofi is friend number two. And Amma is friend number five. Hey, hey. Gotten my numbers. Right? Isaac Bona is friend number one. Kofi is friend number two. And Amma is friend number three. In that order. Meaning that if I am going to write an exam and I have limited time, right, and these three people come to me with problems, I'll take Bona's own first. Like I'll ask Bona, like, if three people come to me with problems, I would focus on Bona first. Then I'll leave the other two because she has the highest priority, right? But what if I ask Bona what's up and Bona says that he's fine? The second Bona says that he's fine, and I move on to service. I move on to friend two. Bona faints. Because of how my system is now, I cannot go back and ask, like, fix Bona's issue. I have to go to Ame's issue first. If Ama doesn't have any problem, now I can go back to Bona to understand. And shout out to Bona. Today is your birthday. Elisa appreciates you so much. A blessing. Let's move on. So that's the device one, device two, and device three. That's how it will work. So the worst case scenario is that the worst case scenario for device 5 is that it just ended and then like it had an issue. But had a microprocessor, you can't ask device 5 like what's up, and then it will tell you and then you can fix the problem. You have to go to device 4, device 3, device 2, and device 1. And what if the device, all the devices are having meltdowns that day? That day wasn't a very, very good day. Asa lost the match. So device 4's time is 2.5. So it will have to wait for 2.5 nanoseconds for device 4 to finish. And what if device 3 also has an issue? 0.92. Let me see. Right. It will have to wait for device 2 to finish. That is 1.1 to 1.2. And have to wait for device 1 to finish, which is 2. You understand? So in the worst case scenario, it have to wait for all these processes to finish. And that sums up to 0.9 plus 1 plus 2. So in the worst case scenario, it will take 6.62 nanoseconds, right? For everything, like in the worst case for device 5, it will have to take 6.62 seconds. You understand? Like that's the worst case scenario. In the best case scenario, device 1 just finished and it's about to start. So it will take 0.00 nanoseconds. That's the best case. So now we are done. We are done with the highest priority device. So how about the last priority device? The last priority device in the worst case is the same thing, and then like it's the same situation, right? In the worst case, what if device one just ended? But in the worst case, what if device one just ended? Right? So it will have to go through device 5, device 4, 3, 2. So this in this case, you have to sum this one up. You have to sum this one up. So in the worst case, it will give you 4.7 if my math is correct. The worst case, right, it will have to give you 4.72 because in the worst case, we assume that device one just finished, it just finished pulling it, and then it moves on to device 5, and then device 1 has a crash. So that means it will have to wait for device 5, 4, 3, and 2 to. And what if they are all having meltdowns? That's the worst, absolute worst situation. The best case scenario that they just finished device 2 and it's problem just happens there and there. That one takes 0 seconds. You are already come to ask me how I am, and then I have a bout of malaria. You understand? That one, perfect situation. I'm ready. Like your mother has called you, and then like that instant you start to feel sick. Oh, you're cashing out big. You understand? So that's analogy you can use for this. Excellent. So that gives you the time that you use. So just Charlie punch in the times and then move. It's not a lot of marks, but by changing our time. Okay, it's 20 marks, actually a lot of marks. A lot of marks. So that's it. So we just finished C. So the deboring ideas from at least one of these processes, x86. So you see the x86 focus is really, really high, right? If you after this stream and you realize that you are able to answer all the previous questions, this is what you should do. What you should do is that go online and read about the history of microprocessors, or go on the Microsoft Teams and then watch the 3 videos he put up. And then after that, go and watch the project. Check the Lisa. So the Lisa is this is the Lisa link for Google Drive. cutt.ly/Elisa Y3, right? Go to this link and then search for the project. So let's do it, right? Let's do it. Search for the project that's your seniors did last, what they did last year, and then please look to the Pentium, look to on the other ones, and try to familiarize yourself with it, because that's basically how all the questions will come out. Right? So there's a some one thing, microprocessors. Yeah. Right? Microprocessors, files, um, presentation. Yes, it's in presentation. And look for them. There are plenty. x86, i5, Pentium 1, XAM. Yes, yeah, yeah. So there are x86, i5, and then Pentium 1 pair. Understand? Look through them and then try to familiarize yourself with them. It will really, really help you think about your answers. And if something that we've not covered comes in the exam, you'll be able to answer. But then, Charlie, Lisa, no, we don't cover things that don't come. So they're asking you that borrowing ideas from at least one of these processes, right? x86, P1, P2. So yes, not going through this in class, right? But the question can still come because Chris told us to. So we have pipelining, right? Pipelining is also the same as um, multi-instruction queues. You understand? That's the same thing as pipelining. You can also have data and code segmentation. Okay, so the P we talked about the Pentium and also ah, okay, so it seems it wasn't connected and I spoke, right? With the Pentium family, this is the Pentium family of processors. Right? Pentium family of processors, the advantage to have over this basic macro architecture is that it will have superscalar architecture, it will have a high level of speed, and it will also have what's the last one? Because in my mind right now, yes. Has level caches, right? It has level caches. Level caches. So you can also write it level caches. These are the advantages that the Pentium family will have over it. So you can so that's how, and you say that, oh, this basic macro architecture does not have data encode segment. Beautiful. Okay, so we are back. Sorry for the yeah, it's very, very bad. That's why. So please let's get back to it. So what I was saying is that you can just skip back a little to know what I was saying. I wanted to explain what the superscalar architecture was. This diagram. That's basically what you have is yesterday we explained pipelining as multiple fetch cycles. The fetch is fetching whilst everything else is going to whilst right whilst you are decoding, you're also fetching. Whilst you are executing, you're also fetching. Whilst you are storing, you're also fetching. So then you have a backlog of instructions that have been fetched. You have a backlog of instructions that have been fetched already. And the thing that makes things slow, right? The thing that makes things slow in like, microprocessor like main microprocessor is that it has to go to memory for information. So if your information is closer to your processor, your microprocessor, that means that you get a faster time. And yesterday when we did the calculations, we got almost more than double, like more than double the time that need for this. The pipeline process gave you like as short almost half the time. Perfect. So let's assume you have a pipeline fetch cycle, have a pipeline execute, and then you have something called a scheduler. We don't care what the scheduler does, but have an execute, have a stop, have an execute, have a stop. Perfect. This is basically how this is basically how a superscalar would work. Meaning that you will fetch more and then you execute more. Understand? Now when it gets to the scheduler would it can be two, it can be three, it can be 300. You don't. It depends on how much you want. Understand? How many execute cycles you're able to afford. So let's say that you fetch, and this one there's something called in order, like in order and then out of order processing. That's what the scheduler does, right? If there are two instructions that follow each other, you can't let them pass through two different execute cycles. So for example, assume that we want to implement this equation. It's in a past question, so don't just think of it as an example. With this, right? No, let's change this one to like f. Assume this is f, right? Y plus f, a plus b. Have variables in the system that are like this. And want to find the solution. Assume this is also like x or something, independent variables. What we can do is that we can fetch both of them. Um, this is supposed to be a decode, or this is supposed to be can decode both of them, and the scheduler can send both of them to the two different execute cycles, and then you see the storage tool will store them into various things, and then we can fetch the next process, and the next process will just add them. Understand? So instead of like taking 3 clock cycles, we've taken 2. I hope you understand why you're taking 2. So the pipeline process makes it extremely fast. Like if you thought pipeline was making it fast, in superscalar there, we don't even go there. It's, so normally it is called super pipeline, right? Because you're just in pipeline, you're just pipelining the fetch cycle. So you can pipeline, decode, execute, store. You understand? That's basically what we're trying to do. So that's what superscalar means. So if it comes out, you'll be able to explain it or you'll be able to lie your way around it, which is the aim. Okay, so please, I was told by the people at the studio that they themselves didn't get it. They themselves didn't get it, and then please lose hope of getting it. Let's go over it again. The person who didn't get it was Kelvin Tamaklu. So for the computer engineers among us, might be more familiar with for the web for the web you call yourselves developers, or for the web developers among us, you might be familiar with this system in terms of a load balancer, right? So if you do backend web dev, you'll be familiar with this, right? Where your site, when you get a requester, transfer it into another, transfer it to another server because you don't want to overload your system. So this is the reason why when WAEC results come out and you're viewing your results, the site can actually crash because it doesn't have what we call a load. So some small computer engineering for you people, you can put it on your CV. Right? So this is what happens when a lot of people are trying to access. So you have YX website sitting on some computer somewhere, some server somewhere, and then plenty, like a lot of people. So what's it like? This is rating by how many? Maybe 5 million people. 5 million people are trying to access the server at once. No matter what kind of processor you're using, it can't compute 5 million different requests at once. You understand? So it has to go to a load balance. What a load balancer is that it's a very, very quick. So yeah, we've already agreed that this is a bad system. What the load balancer does is that we have YX sites sitting on 4 different or 3 different laptops, 3 different servers. What happens is that if 5,000 people, 5 million people are trying to access the site, it will send them to 3 different sites. No, it will send them to the same site on 3 different laptops. Let's put it that way. It will balance the load. It will say that server 1, server 2, Say that server 2 is free. Let me direct your results towards server 3. Then you can check your results through server 3. If server 1 is free to do that. And so that is why Google can never, like Google's plenty requests can never go down, because they have an extremely good load balancing algorithm. You understand? And you go with it with algorithm. So that's basically what the scheduler would do. Yes, the scheduler would balance your load in quotes for you. Right? If you have multiple fetch, so it's sort of like that, right? I keep writing the execute here. What you can do is that you can fetch more, and as you are fetching, so you have a sort of a couple of instruction registers here. So you are fetching into your system, you are fetching into your registers. You're just sending you're just fetching plenty, and then you're decoding plenty too. So you have multiple decoding cycles, right? Now when it gets to the scheduler would say that, oh, follow your, like, did the instruction follow it? So that the scheduler sort to decide that, is this, do they follow each other? Do the instructions, are they capable of following each other, or can be split up? Because some instructions you can never split them up. For example, you have something like y is equal to 2a, and then you have y is equal to 2a plus b. Right? You can't send 2a here and 2a plus b here, because you need the result of 2a. You understand? And you don't have that result yet. You understand? So you need the result. So they need to follow each other. That's something that they need to follow each other. But let's say you have y is equal to a plus b minus b plus f, something like this. You can send a plus b into pipeline, your pipeline one, and send your um your your d plus f into your second cycle, your second pipeline process. You understand? That's basically that's basic. That's what you do. So as I said, none of the questions usually have answers. Most of them are just thinking questions. You have to select what you believe that from your hometown. You believe that superscale architecture always beats pipelining. So you go that route. So when they ask you that, why you pick superscalar, you have to see it, and then you have to define it. You understand? You have to say superscalar does this over pipeline. That's why I like it. But my hometown, I like simplicity. So you might go for pipeline over superscalar. Like, as long as it's simple, no matter, even if it's slow, actually we still move. And some people slow but sure. Understand? So you can pick any of them based on how you think about them. And that's an actual question that has come before. So take notice of it. Yes, so please, I think that is everything. If anything, we'll discuss it on the page. You understand? I thank you so much for the stream. Have a lovely exam, and then please, you'll pass the micro, no fear. It's very, very simple. Pass questions. We thank you so much. Bye bye.